started. It's my pleasure to introduce Professor Yanran Ding. Yanran joined us last year, so he's one of our new professors in robotics. He did his undergrad at Shanghai Jiatong, and he got his PhD in mechanical engineering from University of Illinois Urbana-Champaign. Then he spent some time as a postdoc at MIT. Then we poached him here, and he joined us. As a side note, he's a Michigan grad kid in the sense that his advisors, his PhD advisor is Jesse Grizzle. So he has some Michigan connection there as well. He has won several best paper awards, and now he's going to be telling us what he's up to in Michigan, I guess.
Thank you so much, Nashmir. Yeah, it is my great pleasure to be presenting in the control seminar. And today I would like to talk about optimization-based control and planning for Agile like the robot. So my name is Yanran Ding. I'm with the Department of Robotics. I joined last year, and I'm leading the Agile Robot Control and Design Lab. And many of my students are here today. So first, I want to kind of motivate why we need leg robot, right? So leg robot has this unique capability to make discrete contact with the environments, which makes them extremely useful in scenarios with unstructured terrains. For example, in firefighting scenarios, search and rescue missions after an earthquake. And if you think back to the Fukushima nuclear disaster, if we could have the capability to send leg robots autonomously into the nuclear disaster, then we can close the valve and reduce the damage. And in the past pandemic, we have seen leg robot to be applied in the fight against COVID-19. In this picture, the Spot robot from Boston Dynamics has been used as a telepresence platform for the doctors in hospitals. And projecting into the future, we can see that due to the lack of labor in the future, probably one potential solution is to use leg robot in home care scenarios where they will be doing chores for us or taking care of us in the future. Okay, so let's first take a look at the search and rescue scenarios where I mentioned that leg robot has a special capability to make discrete contact with the environment. And in the first project I'm going to present, it's about the jump planning over rough terrain. So if you imagine that in a collapsed building after earthquake, if we can send in leg robot that can make a sequence of jumps to overcome these rough terrains, we can do search and rescues to identify the survivors. So the planning problem has a couple of challenges. One of them is that they have to reason about discrete decisions because the terrain presented to the robot is not a smooth terrain. It has multiple patches that it can make contact with. So it has to reason about at which time to be in contact with which patch of terrain. The second challenge is that it has to do continuous time optimization because the system undergoes very agile, highly dynamic motions. It has to explicitly reason about its capability limit as well as the complexity imposed by the environment. So the first project is about jump motion planning in unstructured terrain, and specifically, we're using mixed integer convex optimization. So the problem is set up as follows. Our goal is to enable the robot to come up with a motion plan that leads the robot from the starting position to the goal region through a sequence of jumps. So in order to make the problem a little bit easier, we make the following assumptions where we assume that all the motions are planar. And we assume that the robot's leg is having very little mass, and almost all of the mass is lumped in the torso, so we can use a point mass model for the planning. We also assume perfect state observation and terrain information to be perfectly known because this long sequence reasoning is hard enough, right? With the point mass model, you can think of it as planning with double integrator. Given a ground relation profile, we can integrate twice to obtain a trajectory of center of mass velocity as well as its position. However, the difficulty lies in its constraints. So the first constraint, which is the friction cone constraint, is quite benign because in order to ensure the foot does not slip with respect to the ground rotation force should be lying within this cone, right? But luckily, this constraint is linear in nature and doesn't break the convexity of the problem. So the problem comes in when we want to introduce torque limit constraint. The torque limit constraint is a non-convex constraint because even with the massless lag assumption, the torque is equal to the Jacobian transpose times the force, which is the workspace, the ground rotation force. And the Jacobian matrix involves the sine and the cosine functions and breaks the convexity. The second source of non-convexity comes from the bilinear constraints in the flight phase kinematics. So if we take a look at the jump from jump, the robot will undergo an aerial phase where the takeoff velocity P dot TO and the aerial time TR are both decision variables, and this equality constraint is bilinear. And of course, even with the simplified terrain assumption, in the choice of foothold is in nature discretized. So we have to introduce mixed integer constraint into the mix. So by looking at this problem statement, we can pretty much conclude this can be naively formulated as a mixed integer nonlinear program, or MINLP, which is very difficult to solve, if ever possible. So our question is that, can we do a little bit better than MINLP in this case? And the proposition we have is that maybe we can relax it to make it at least mixed integer convex. So the main idea to make this MINLP convex is first starting with discretizing the workspace, or the configured space of the robot, or the C space. The reasoning is because the torque limit constraint is conditioned only on the pose of the robot. And if we can discretize the C space, then we can transcribe the original non-convex constraint into a set of mixed integer or piecewise convex constraints, right? So the first thing we do is to discretize the C space into a collection of convex polytopes. And then we introduce binary variables to kind of act as switches to activate or deactivate the piecewise convex constraint associated with specific polytope. So specifically, we assign a binary variable indexed by S and T for each polytope omega S at time T, where if the binary variable BST takes the value of 1, that means at time T, the center of mass position P is in polytope omega S. And whenever that happens, the associated convex constraint with that polytope will be activated, and all the other constraints will be deactivated. So B here is a binary variable, and if we add the additional equality constraint where the summation of the binary variable along the axis of space is equal to exactly 1, then we can make sure that only one polytope is activated, which means that at any given time T, the center of mass of the robot will occupy exactly one polytope. So here, the implies operator, which is this right arrow, is implemented using the began formulation. All right, so this is the setup. We have discretized the convex, we have discretized the workspace and introduced the binary variables in hoping that we can transcribe the MINLP into a mixed integer convex program. So now, how can we obtain a convex relaxation of the non-convex constraint associated with a torque, associated with a specific polytope? So let's take a look at this torque limit constraint. So for each polytope, the torque limit constraint can be written down as follows, where the 2 norm of the torque vector tau should be less than or equal to tau max, where the torque vector is a 2x1 vector with the hip and knee torque. And the torque is Jacobian matrix transpose times F, where F is the ground rotation force. And the joint angle Q can be calculated from the center of mass position via inverse kinematics, right? So we can call this torque limit constraint star, and by plugging the third equation into the second and the second to the first, we can rewrite the torque limit constraint as follows, So the 2 norm of J transpose F squared is less than tau max squared. And if we write it in quadratic form, the torque limit constraint is a quadratic inequality constraint. So let's take a closer look at one specific polytope. So our goal is to obtain a convex relaxation of the non-convex torque limit constraint for all the points within this polytope. A very natural idea is at least we need to satisfy star at the 3 vertices, right? So we can write down this 3 set of inequality constraints by, plugging in the associated Jacobian matrix Ji into the inequality constraint. So here we observe that the matrix J times J transpose is corresponding to a ellipsoid epsilon I in the joint torque space. So if we draw the torque ellipsoids in the joint torque space, for each of the vertices, we can see that we have 3 ellipsoids. And what this inequality constraint says is that all 3 ellipsoids should be lying within this circle with radius tau max. So now the question is, how do we generalize from these 3 vertices into all points within this polytope, right? Because if this is finite sample, how do we make sure that we can satisfy this constraint for all the points? One idea is to simply take more samples within this polytope, so we can take 0.4, 5, and so on, and then add to the list, but it's not exhaustive, right? So how do we make sure that we generalize? Well, we propose to use a convex relaxation where we impose the torque limit constraint star on the minimum volume ellipsoid that covers the union of ellipsoids, right? So if we can find a ellipsoid that covers all ellipsoids sampled, and then instead of imposing on each sampled ellipsoid, we impose the torque limit on this kind of overestimation of ellipsoids, then we can make sure that the torque limit constraint is guaranteed within this polytope. So now the question becomes how to find the minimum volume ellipsoid given the set of sampled ellipsoids. And it turns out we can use the Lohner-John ellipsoid. And the Lohner-John ellipsoid can be obtained by solving a semi-definite program or SDP. So in this SDP, the decision variables is X, which is a 3x3 symmetric positive definite matrix corresponding to the ellipsoid of interest, which is the blue ellipsoid on the lower left corner. We want the minimum volume of this ellipsoid, so we want to minimize the trace of this matrix S, X, and then we want the ellipsoid to cover all the sampled ellipsoids. So we need to make sure that X is greater than or equal to Ji times Ji transpose for all the sampled ellipsoids, right? So this SDP can be solved using solvers, and each Jacobian is the Jacobian matrix at the vertex points. So we can solve the SDP to obtain the X matrices. And instead of imposing the torque limit on the sampled points, we impose the torque limit into this overestimation of torque mapping. So at this point, we have transcribed the original non-convex constraint into a mixed integer quadratic constraint. Any questions up to this point? Yeah.
So this Lohner-John ellipsoid semi-definite program, it only involves the torque ellipsoid at the 3 vertices, right?
Yes.
And that you know that all the other ellipsoids are within.
Yeah, so this is a very good point, right? So it depends whether this assumption holds depends on how you discretize the space, right? We know that binary variable is quite expensive, so we want to minimize the number of sections, but we want to make sure the section is small enough that this holds. So it's like a trial and error process that you'll figure out what the hyperparameter is. Okay, so solving this SDP is computationally expensive, but the good news is that it can be done offline, right? So we can construct this C-space discretization, solve a bunch of SDP for each ellipsoid, and then retrieve those X matrices online for the planning. Okay, at this point, we have, convex friction cone constraint, and we have transcribed the originally non-convex torque limit constraint into mixed integer convex constraints. So another source of non-convexity comes from the bilinear constraints in the flight phase kinematics. And the flight phase kinematics is bilinear, and the way we deal with it is to introduce a McCormick envelope approximation. So the graph on the lower left-hand side is the surface correspond to the product of takeoff velocity P dot TO times the aero time T air. This is a non-convex constraint, as you can see, and the way we tackle this is that we discretize the surface into finite set of convex polytopes and introduce additional binary variables to activate and deactivate the constraints. So this looks a little bit, so it kind of transcribed this original surface constraint into like a bubble wrap. So each of the segment corresponds to a pouch, and the binary product will be lying within one of the pouch at any given time, right? And for the foothold choice constraint, we introduce additional binary variables because we model the terrain as piecewise affine functions, and at each jump, we allow the solver to decide which segment of terrain to choose. Okay, so at this point, we have formulated the original mixed integer nonlinear program into a mixed integer convex program, MICP. And this problem can be solved for this particular setup where the robot is commanded to jump from the starting point to the goal, which is on the high platform. And the robot doesn't have the high enough torque to directly jump from the starting point to the goal region. So we introduce additional terrain feature on the left-hand side, hoping that it will figure out the strategy to utilize the terrain on the left-hand side to reach the goal region. And it turns out that this MICP formulation is able to be solved within 1 second using CPLEX a few years ago to figure out the solution by itself. So here we do not supply any additional initial guesses or warm start. So the program is able to figure out by itself. And by integrating with a hardware system we developed, we have replicated this behavior in experiment. So here we have like a boom system to kind of planarize the motion of the robot. And then we have a good enough low-level torque control to execute the motion. So now we can kind of plan this sequence of jump for a single-leg robot. A natural question to ask is whether we can extend for multi-legged robot. And it turns out we can do so. The difference between a single-leg robot and this two-leg robot is that we have more contact foot capabilities. So we introduced the notion of feasible wrench polytope, which is the intersection of the contact wrench cone, which is the friction cone as we have introduced before, as well as the actuation wrench polytope, AWP, which is the mapping from the torque limit in joint space into the workspace. And the FWP is the intersection of these two polytopes, and it represents the actuator and environment constraints in one polytope. So a formal definition of FWP is that have two components. One is the linear force, and second is the moment about the center of mass. For one FWP, it's relatively easy to represent, but if both of the foot are in contact with the ground, then the FWP of two legs is the Minkowski sum of the two FWP corresponding to the contact foot. So here's a visualization of what that looks like. Here, the blue polytope represents the FWP associated with the front leg, and the red corresponds to the FWP associated with the back leg. And if we plot it in the wrench space, Fx, Fz, and tau y, then we can see that the FWP of each foot is slanted because the front foot can produce wrench only in a subspace of the wrench space. However, if we sum up these two FWP to get the FWP of the two legs, we can see it's a convex three-dimensional polytope. So the reason why we want to optimize within this FWP space is because originally we have relatively complex dynamics, right? The complexity meaning coming from this cross product, R cross U, where R is the vector from the center of mass to the contact position, and U is the ground reaction force. And in addition to that, we also have complex constraints where we have encountered the torque limit constraint as well as friction cone constraint. So by introducing this FWP, we can transcribe the original problem into simple linear dynamics, because now our optimization variable becomes the range around the center of mass, and we move the complexity into the FWP construction. The reason why that is beneficial is that we know that in mixed integer program, it is introduction of the additional binary variable that's expensive, right? It doesn't scale well in the dimension of binary variables, but the complexity of the constraint associated with a binary variable doesn't scale badly, right? So we want to pack as much complexity into one binary variable as much as possible. So that's the main idea. So what does the C space of the robot look like? So it looks like this. It has 3 sections. Each section corresponds to one contact condition. The red one is when the robot only has back foot in contact with the ground. The blue one, the front foot, and the black region correspond to double stance. And as before, we discretize this C space into a finite number of tetrahedrons in this case. And then we introduce a binary variable BST for each configuration Q, which is the central mass position and pitch angle. So whenever a binary variable is equal to 1, it means that the configuration of the robot lies within this tetrahedron omega s, and the associated range constraint is activated. And as before, we have this summation to 1 constraint to ensure that the configuration of the robot will only lie within one tetrahedron at one time. And similar to before, the implied operator is implemented using big M formulation. So here are some videos showing that the execution of these motion plans, the robot can jump up forward onto a plane, jump backward onto a plane, as well as figuring out this relatively complex parkour motion using a bit of time, 27 seconds. But it is relatively complex because it's reasoning about the terrain choice as well as the context sequence at the same time. Okay, so here concludes the first part of the presentation, which is about motion planning for jumping robot. Any questions? All right. So next, I'm going to talk about optimization-based control for dynamic leg robots. So we have those motions. How can we control them? The method that we use here is optimization-based control. The main idea is that we formulate a control design problem as an optimization problem based on a model of choice. So here, we want to minimize a cost subject to constraints, where the constraint is conditioned on the model that we choose. So for leg robot, because of its high dimensionality and hybrid nature, we usually choose a simplified model to capture the dominant dynamic effect of the robot. And another additional benefit is that a model is interpretable. So for example, for a quadruped robot, we often model it as a single rigid body. So you can think of it as a floating potato with contact forces that juggles it, right? So contact forces will be activated whenever the foot is in contact with the ground. So all models are wrong, but some are useful. In this case, this single rigid body model is quite useful. So the formulation of MPC, or model predictive control, is as follows. At each moment of time, we measure the current state of the robot X. And then based on this measurement, we formulate a optimization problem. For example, we can formulate a quadratic program where we penalize the state tracking error and control effort subject here to linear constraints that encodes the dynamics, which comes from the model, as well as the inequality constraints imposed by the environment, for example, friction cone constraint. And then the output of this optimization is a sequence of action prediction as well as state predictions into a future within a horizon. And we only apply the first optimal input during the current time t and the next time tick. Until the next time comes, we do this whole thing again. So you can think of this MPC formulation as a linear quadratic regulator, or LQR, with inequality constraints. So the benefits of MPC is that it's a declarative policy, which means that you can articulate what you want and impose it as constraints. And it's also safety fenced by the inequality constraints. And because it's based on the model, it inherits the interpretability from the model. So traditionally, quadruped robot, MPC for quadruped robot uses Euler angles to represent its orientation. But Euler angle has the trouble of singularity, because as you can see in this figure, whenever the two rotational axes of Euler angle are collinear, then we lose a degrees of freedom, which correspond to the gimbal log or singularity of a matrix. And what that means numerically is that whenever the robot, in this case, the pitch angle is close to plus minus 90 degrees, the MPC will experience numeric instability. There's also quaternion that can be used to parameterize the orientation of the robot, but it does have the double covering issue, which means that for each orientation, there are two distinct quaternions, which can be problematic if you want the robot to execute motions with large angular excursion. So we propose a MPC formulation with that directly works on rotation matrix instead of Euler angle or quaternion. And by doing so, we can unlock new behaviors without additional computational requirements. And here we see controlled backflip. So the way that we do MPC with rotation matrix is that we linearize the original nonlinear rotational dynamics R dot equal to R times omega hat. And we basically take the first order Taylor expansion of the matrix exponential map. So imagine that the rotation matrix R lives on the SO3 manifold. And at each time t, we can measure the current orientation RT, and we take the tangent plane around the current orientation RT, and then we predict on the tangent plane. And because the variables RT, the variables delta RK are a 3x3 vector, a 3x3 matrix, we need to vectorize it to fit it into the MPC formulation. Once we have done so, we can use forward Euler integration scheme to obtain our discrete time linear dynamics. So up to this point, we have linearized the nonlinear rotational dynamics. Another piece of the puzzle is the objective function. The original orientation error function involves matrix logarithm map. So here, RD is our desired orientation we want to track. RT is our current orientation, and RK is our predicted orientation, K steps into the future. And ER is the geodesic between RD and RK. And this involves matrix logarithm function, which is nonlinear. But we want linear expression for the orientation error. And the way that we approximate ER is to decompose it into two parts. The first part is the geodesic between RD and current orientation RT. And the second is the linear approximation delta RK. And by doing so, we obtain a linear expression for the orientation error. And the orientation cost consequently becomes quadratic. So we have a linearized dynamics and a quadratic cost function. At this point, we can formulate the MPC problem as a quadratic program. And even if this MPC problem is a high dimensional problem, we can exploit the sparsity of this problem. So in this case, the Hessian matrix of the cost is a diagonal matrix, and the Jacobian matrix of the equality constraint is block diagonal and block tridiagonal. And we can exploit this sparsity pattern in our custom QP solver called QP Swift to solve the MPC problem at 200 Hertz and above. So using this MPC, we can perform a variety of quadruped behaviors such as pose control, trotting, and so on. So this video was published in 2021, which looks like really vintage at this point, and this shows that the rapid advancement of the field. Okay, a special feat enabled by the MPC using rotation matrix is a controlled backflip. So in this controlled backflip, the robot has to go through the singular pose corresponding to the pitch angle equal to 90 degrees. And as you can see in this video, on the lower right side, the Euler angle representation will experience a sudden jump, will destabilize the MPC using Euler angle, but because we're using rotation matrix, it doesn't get affected. And we have open sourced the code, RFMPC, on the GitHub. Okay, so these are the MPC work that I've done with the quadruped robot. And we can see that in the past years, we have seen a lot of advancement in the field, especially in quadruped robot, exemplified by the MIT Cheetah robot series. So the robot that I work with, Panther, came out about the same time the mini cheetah came out. And after that, especially in the past 2 years, starting from the end of 2022, we have seen a rise of humanoid, where there are a lot of companies that's coming up with their own humanoid as well as research labs as well. So the next portion of this presentation, I'll talk about a little bit about my experience with humanoid control on the MIT Humanoid. So the MIT Humanoid hardware is quite magnificent in the sense that it has 18 degrees of freedom. Each leg has 5 degrees of freedom, and the arm has 4 degrees of freedom. And the total mass is 24 kilograms. Each of the joints is using a so-called quasi-direct drive actuator model, and its max torque is quite impressive, especially the knee can reach up to 140 Newton meter. This is impressive because the reduction ratio is only 6:1 for each joint. So the difference between humanoid and quadruped, I would say, is that for humanoid, the footstep location selection is much more important because for quadruped robot, it has 4 feet and its stepping frequency is relatively high. But for humanoid, it only have 2 feet and stepping frequency is relatively lower. So choosing where to step is much more important. So in addition to the previous single rigid body model that we used for the quadruped control, here I introduced the augmented single rigid body model where I added the footstep location as part of the state vector. And the benefit is that now we can reason about the torso orientation and the stepping strategy simultaneously. Specifically, how we do that is we add an additional term into the linear dynamics, where the A matrix is nothing but a Jacobian of the dynamics with respect to the state, where the state includes the single rigid body state X and footstep location C. And the last 3 columns of this A matrix called AC characterize how a change in the step location C will affect the dynamics. And we add this AC matrix as an additional term into the linear dynamics. And here, eta is a binary vector that encodes the gate sequence, the gate schedule, to turn on and off the capability to take a step. And delta C here is the stepping vector, which is part of the optimization variable. Okay, so by introducing delta C as part of the MPC variables, we can simultaneously get the ground direction range as well as the footstep policy. A major advantage of using MPC compared with other control methods that's based on inverted pendulum is its capability to impose kinematic constraints and also reason about terrain features. So for example, the footstep length constraint can be easily written down as a inequality constraint where the norm of the step vector delta C can be bounded. And similarly, the leg extension constraint can be bounded as well, where R is the vector from the center of mass or the hip position to the foot location. We can also incorporate local terrain information by taking the first order approximation of the terrain. So the robot has an ankle joint, and by measuring the ankle angle, we can have a local approximation of the terrain and plan according to that. And as you can imagine, as the robot takes a new step, it has a new measurement of the terrain, and it can update the terrain constraint accordingly. In addition to the MPC, we also need a whole body controller that reasons about the full dynamics of the robot. So the whole body controller has 3 components. The first one is it leverages the foresight from MPC because whole body control is a myopic controller. Even though it can reason about the full dynamics, it doesn't have a notion of horizon. So MPC will kind of inform long horizon reasoning into the whole body control by introducing a tracking cost in the whole body control. And the second component is the capability to explicitly reason about full body dynamics, and it's manifesting itself as the manipulator equation, as you can see here. And the third part is respect physical constraint. So here, JC is the Jacobian for the contact points. Whenever a contact is happening, its acceleration should be 0, and also the torque limit, as well as friction cone constraint, and so on. So one key contribution of this work is to introduce self-collision avoidance using control barrier function. So robots, especially powerful robot like MIT Humanoid, we don't want it to slam into itself because it can damage the robot and takes long time to repair. So in order to avoid self-collision, we cover the robot first with capsule geometric primitives. And then for each pair of capsule, we write down the sign distance function, Hij. And then the self-collision avoidance constraint becomes that the Hij should be always greater than or equal to 0 at all time. And the control barrier function ensures that the pair of capsule geometric primitive does not collide into each other. And by imposing this as an additional inequality constraint in the whole body control, we can avoid self-collision. On the left-hand side, we can see without the control barrier functions, the robot will collide into itself, and the corresponding part will be highlighted in red. And on the right-hand side, we can see that with the CBF-based collision avoidance, the robot does not slam into itself. And then we put the robot on a wave field. So the blue dot you can see is the footstep prediction based on the local terrain approximation. And the red line is the ground reaction force. And finally, we put the controller onto the physical robot, and it starts to take steps. Okay, so this controller is also robust to some external pushes. Yeah. All right, so that concludes my talk. I'd like to play some of my favorite clips and take any questions. Thank you.
Yes.
Yeah.
So you're doing MPC on SO3. And if I understand what you said correctly, you're doing this by just a forward Euler approximation to sort of linearize the dynamics. But of course, that means that immediately your linearized dynamics go off of the SO3 center. Do you make any effort to project back on the manifold in the trajectory, or do you just accept that there's going to be an error?
Yeah, so in this particular work, we do not project it back into the SO3 manifold, but we do have a discounting factor. So the further away you are in your prediction horizon, the less you trust the orientation prediction.
That was going to be my next question, was whether this limits your horizon.
Yeah, I think so. I mean, there's some subsequent work following this work where it's utilizing a nonlinear MPC formulation. So basically, instead of solving a QP with linear time invariant dynamic system, is solving a LTV system. Basically, it takes the previous trajectory prediction as your reference and then linearize around that. That will mitigate to some extent the SO3 prediction errors, but in any case, it's leaving the SO3 manifold anyway. Yeah. Yeah.
At the end, you had showed this cool video when you really found the region of attraction of the controller, right, in the robot. And then, so what I noticed is that, and this is probably true for bipeds, typically, is that in order to kind of do something, the bipeds kind of walks on a single spot, right? Now, if you would try to perform this test on me, maybe I would be not as good as the robot in terms of disturbance rejection, but I don't have to walk all the time, when I'm standing there. So my question is that, is it still an issue to kind of transfer from like standing to walking or standing to, so how does that work in these robots? It's a little bit of a higher level question.
Yeah, so currently it's specified by the gate schedule. So gate schedule is a vector of binary, numbers that specify whether the foot is in contact or stands. So if you want the robot to stand, you set two vectors of all ones to each leg, so the robot will stand. If you want the robot to walk, you encode the gate pattern into the binary vectors. So the same MPC controller can achieve multiple gates. So as you can imagine, it can walk with really long double stands or walk with really short double stands is all possible.
And what would happen if I make it stand and then I push it?
Oh, yeah, then we will kind of need a state machine. So you have to set a state transition condition. If your center of mass velocity is greater than some threshold, then you have to take a step, right? So it can be done using FSM.
Thank you.
Yeah, I can ask a quick question.
Yeah.
You are using all model-based techniques, and there's now this friction between model-based versus learning. How good your models are supposed to be for these things to work, and do you see any benefit of using something data-driven, and if so, where do you think it will help most?
Well, that's a very packed question. So let me try to decompose a little bit. So so the quality of model or the merit of the model depends on the system. So for Quardruped, single rigid body is a really good model because really all the actuators or the major masses are in the torso. So it's really good approximation. But this assumption kind of start to break down if you take a look at the humanoid robot, because the humanoid robot has relatively heavier limbs. So in this case, single rigid body no longer serves the MPC well. So we can see some need to introduce whole body control. So for Quardruped, it can work without the whole body control at all. But for humanoid, you kind of have to have a really reliable inverse dynamics controller. So that's that. So the rise of data-driven method, definitely I can see it has huge values. And one of my research direction is to attempt to incorporate data-driven method with model-based control. Yeah. But I'm not sure specifically where that is best utilized. We are still in an exploring phase. Yeah.
More questions there?
Yeah.
Maybe let me ask a follow-up question. It's like the beginning, you talk about discretizing the space and formalize it as an optimization problem. Maybe in that part, if we ignore this, then we can produce a continuous virtualization, and you have optimization on top of that, then you can maybe directly tackle the non-convex problem. Have you tried that, or like what would be the bottleneck?
Yeah, so that's a really good point. So looking back, so the planning work is quite a few years back. So I can see a lot of things that can be improved. Yeah, definitely. At that time, I was not aware. I was oblivious to neural networks. So I would like to explore the possibility to introduce learning-based methods in these planning problems.
Thank you.
Yeah.
Yeah, in the beginning, you talked about how you're approximating it as a point mass, like rather than a leg. Obviously, with most of the mass centered at the torso. Did you do that as well in the humanoid modeling, and when does that sort of break?
Yeah, so for the humanoid modeling, we're using a single rigid body model. So you can think of it as a rigid box that's floating in space, and the control effort is the wrench applied from the contact foot. So in this case, we have a line contact, so we can apply pitch torque, yaw torque, but not the roll torque. Yeah. Yeah.
I have more of a speculation question. It goes back to the first part of the talk. You convinced me that jumping opens a lot of new dynamic behaviors, but the thing that is worrying me is if you find me at a disaster scenario, you would never see me jumping, because I would be so scared if I jump, I'm gonna slip or like. So do you think this jumping behaviors could be reconciled with disaster scenarios where you're gonna jump somewhere and then the slope is gonna change all of a sudden?
Yeah, that's a good point. So in this specific kind of motivation for this project, we are envisioning like tiny robot, right? So a very lightweight robot that's not going to kind of move a slab of concrete or stuff like that. So it's more for going into the cracks and the tunnels where human is really hard to reach and to see whether there are survivors there or not. So in this case, I think using jumping motion probably is good, because the lightweight robot will probably be smaller in scale. So in order to kind of overcome this complex terrain, it has to jump in some sense.
Okay, let's thank Yanran again, and if you have more questions. Please ask your question.
Not that long, so it's bad,
You still have fun multi-agent systems?
Not really.
That's hard.
We had a problem that was a multiple traveling salesman problem.
It's kind of trivial for the participants.
Yeah, it's the exact same. I'll see you later. Yeah, no problem. We'll text you. Okay, yeah, sounds good.
Depends on the application, like whether you can benefit more I mean, it's a trade-off between like durability and work density, right? So it's an optimization problem at the end of the day.
Did you want to have?
No, so in the humanoid, we do not, we try to have
Do something else.
but it tweaks so quickly, it doesn't work at all.
Whereas the other maybe you know
Yeah.
you know the one in the mind.
There's a video coming out a few days ago that's really impressive, where the humanoid robot is able to do very human-like locomotion with a heel toe. That's really cool.
Yeah.
Yeah.
I don't know, you'd have to ask Najmi because she has a joint point. I'm not involved in it, so.
No, not really.
Let's also see.
Sure, yeah, that's a fact to the scheduling. You have this exactly.
Engineering college has been adjusting because the other departments lost faculty and we compete for students and, yeah. And Najmi only moved. But that means